In 1940, America prepares to arm the free world against Nazi Germany, while being 100% dependent on Sweden, a neutral country trading with Hitler, for the one component every tank, plane and truck needs to function: ball bearings. Without them, gun turrets seize, aircraft engines explode, and landing gear collapses on impact. The Pentagon calculates that one B-17 Flying Fortress requires 540 ball bearings just to leave the ground. America needs 86 million bearings per month to meet wartime production targets. German U-boats patrol the Atlantic, hunting the Swedish cargo ships carrying this microscopic piece of steel that determines whether democracy survives or falls. This is the untold story of how a small Canton, Ohio company's radical tapered roller design didn't just solve a supply crisis, but gave American machines a 300% longer operational life than their German counterparts. Without this breakthrough, the Sherman tanks rolling through France and the B-29s bombing Tokyo would have broken down before reaching the battlefield. Watch until the end to discover how a 40-degree angle change in a steel cylinder became the secret weapon that won World War II. Every machine in America's arsenal depends on one thing: reducing friction between moving parts. When a tank turret rotates to target an enemy position, when a bomber's propeller spins at 2,800 RPM, when a jeep's wheels turn across a muddy battlefield, bearings make it possible. These small steel spheres sit between surfaces that would otherwise grind against each other until they weld together from heat and pressure. Without bearings, metal on metal creates temperatures exceeding 800 degrees Fahrenheit in seconds. The bearing is the difference between a functioning war machine and a 6-ton paperweight. Military engineers calculate the numbers, and the math is terrifying. Each Liberty ship needs 11,000 bearings in its propulsion system alone. Every P-51 Mustang fighter requires 214 precision bearings in its engine, control surfaces, and landing gear. A single M4 Sherman tank contains 792 bearings throughout its drivetrain, turret assembly, and suspension. The Army's mobilization plan calls for 5,000 tanks in 1941, ramping to 25,000 by 1943. The Navy wants 200 destroyers, 88 aircraft carriers, and 2,700 Liberty ships. Boeing promises 12,731 B-17 bombers. Ford commits to producing one B-24 Liberator every 63 minutes at its Willow Run plant. American industry can build the steel hulls. Factories can forge the armor plating. Workers can rivet the fuselages. But every single vehicle, vessel, and aircraft stops dead without the millions of tiny steel balls that must be manufactured to tolerances of 1/1000th of an inch. A bearing just 0.003 inches out of specification will fail within 40 operating hours, potentially killing everyone depending on that machine. Here's the catastrophe. America produces exactly 0 ball bearings in 1940. The entire industrial base relies on imports from Svenska Kullagerfabriken, SKF, the Swedish monopoly that controls 60% of global bearing production. German-owned factories supply another 25%. America's dependence on foreign bearings is absolute and terrifying. When President Roosevelt signs the Lend-Lease Act to arm Britain and the Soviet Union, military planners realize they're promising weapons filled with components controlled by neutral Sweden and enemy Germany. On April 9, 1940, the crisis becomes real. Germany invades Denmark and Norway in a lightning campaign that takes 6 hours to secure Scandinavian ports. Nazi forces now sit 300 miles from Sweden's bearing factories. Hitler's military understands the strategic value of SKF's production better than America's generals do. German intelligence already maps every Swedish freighter carrying bearings across the Atlantic. Kriegsmarine submarines receive orders: sink any vessel transporting bearings to Allied ports. Within 48 hours of the Scandinavian invasion, 3 Swedish cargo ships disappear in the North Atlantic. British destroyers find one, the Lagerholm, burning from stem to stern after a U-boat torpedo strike. Its cargo manifest lists 340,000 ball bearings destined for Detroit automotive factories. Those bearings rest in 2,000 feet of freezing water, representing 1 month's supply for American tank production. The Royal Navy reports that convoy routes from Sweden now require 4 destroyer escorts per merchant vessel. Insurance rates for bearing shipments increase 900% overnight. Several Swedish shipping companies refuse American contracts entirely. American factories feel the shortage within 2 weeks. Chrysler's tank assembly line in Detroit schedules production of 600 M3 tanks in May 1940. They receive bearings for 173. Ford's Willow Run facility prepares to manufacture bomber nose gear assemblies. The precision bearings needed for retractable landing gear don't arrive. Boeing's Seattle plant has 47 partially completed B-17s sitting on the assembly floor, waiting for engine bearings stuck somewhere in the Atlantic. Production engineers watch their carefully planned schedules collapse. The bearings that do arrive often show damage from rough handling during high-speed convoy evasion maneuvers. Saltwater corrosion ruins 15% of shipments. By June 1940, the situation turns desperate. France falls to Nazi Germany in 6 weeks. Britain stands alone against the Wehrmacht. Churchill cables Roosevelt begging for weapons, equipment, anything to prevent invasion. The American War Department commits to supplying 14,000 aircraft to Britain by 1942, but the math doesn't work. Current bearing supplies allow for 3,200 aircraft. The shortfall is catastrophic. Warehouse inventories drop to 0. Military procurement officers scramble to find alternative suppliers, offering triple the market rate for any bearing manufacturer. They discover why Sweden's SKF became a monopoly. Ball bearing production requires extraordinary precision tooling, metallurgical expertise, and quality control that takes years to develop. The American bearing industry consists of 4 small companies producing bearings for civilian applications like bicycles and industrial machinery. Their total capacity equals 4% of military requirements. Their quality standards can't meet military specifications. A civilian bearing might last 800 operational hours. A military bearing in a bomber engine must survive 2,400 hours at extreme temperatures and vibrations. Without bearings, the Liberty ship program will fail. Without Liberty ships, Britain will starve under German U-boat blockade. Without weapons reaching Britain and the Soviet Union, Nazi Germany will control all of Europe. The Pentagon estimates that current bearing supplies will sustain full military production for exactly 91 days. After that, American factories will go silent while Hitler's panzer divisions roll across Russia. Something had to change, fast. The Army Corps of Engineers launches an emergency bearing development program in July 1940. Their first solution seems logical: copy Swedish ball bearing designs and mass-produce them in American factories. Engineering teams disassemble hundreds of SKF bearings, measure every dimension, and analyze the steel composition. They reverse-engineer the manufacturing process, document the precision grinding techniques, and create blueprints for American production. General Motors receives a $7 million contract to build a dedicated ball bearing factory in Saginaw, Michigan. Engineers install German-made grinding machines purchased before the war. They hire metallurgists from American Steel and Wire to develop the correct bearing-grade alloy. Workers begin producing ball bearings in October 1940. The first production batch contains 10,000 units destined for Wright Cyclone aircraft engines. But within 300 operating hours, the bearings fail catastrophically. Pilots report rough engine vibration, followed by complete seizure. Investigators discover that American bearing balls vary in diameter by 0.007 inches, 7 times the acceptable tolerance. The hardening process leaves inconsistent surface properties. Under the extreme loads of military service, these imperfections cause rapid wear. Metal particles contaminate the lubricating oil, creating a grinding paste that destroys the bearing races. The catastrophic failure rate hits 34%. No pilot will fly with components that have a 1 in 3 chance of killing them. The Army rejects the entire production run. $7 million and 4 months vanish into scrap metal bins. Military procurement turns to desperate alternatives. Could ceramic bearings work? Engineers at Norton Abrasives attempt to manufacture bearings from silicon carbide, the same material used in grinding wheels. Ceramic offers hardness advantages over steel and doesn't require imported Swedish alloy formulas. Laboratory tests show promise. The ceramic bearings survive extreme temperatures that would soften steel. They resist corrosion from saltwater exposure. Initial friction tests indicate good performance. They install ceramic bearings in a Pratt & Whitney R1830 twin Wasp engine and run it on a test stand. The engine reaches 1,000 RPM smoothly. At 1,600 RPM, engineers detect unusual harmonics in the vibration sensors. At 2,100 RPM, a sound like a rifle shot echoes through the test facility. The ceramic bearing shatters under the cyclical loading, sending fragments through the engine like shrapnel. The $85,000 test engine becomes unrepairable scrap. Ceramics lack the impact resistance to survive the instantaneous shock loads when an aircraft landing gear hits a runway at 90 miles per hour, carrying 30,000 pounds. They experiment with bronze bushings as a temporary substitute. Bronze bearings were good enough for locomotives and industrial machinery in 1910. Perhaps older technology could bridge the gap until Swedish shipments resume. The Bronze Bearing Division of Bunting Brass and Bronze Company supplies 50,000 bronze bushings for testing in tank transmissions. The bronze bearings reduce friction better than no bearings, but they can't match ball bearing performance. Under combat loading conditions, bronze bearings wear 16 times faster than steel. They generate 3 times more heat. Tank transmissions require complete bronze bushing replacement every 120 operational hours. In combat conditions, that means replacing bearings after every 3rd mission. The logistics become impossible. Engineers try improvising with captured German bearings. American intelligence services acquire 3,000 German bearings from a damaged U-boat recovered off the coast of Iceland. Investigators discover that Nazi Germany faces similar bearing shortages. German bearings show signs of reduced quality, simplified cages, slightly looser tolerances, marginal materials. Germany's bearing factories are being bombed by RAF raids. Their Swedish supply line faces the same U-boat risks as America's. This revelation is simultaneously encouraging and terrifying. If Germany struggles with bearing supplies, their war machine has vulnerabilities. But if America can't solve the bearing crisis better than Germany, the winner will be whoever manages scarcity most effectively, not whoever innovates. Morale collapses as each attempt fails. Production engineers watch assembly lines idle for lack of components smaller than a marble. Workers at defense plants receive layoff notices because completed aircraft can't be delivered without final bearing installations. Military brass discusses reducing equipment quality standards to accept higher failure rates. Some generals propose accepting 25% equipment losses as unavoidable. The human cost behind that percentage haunts the Pentagon. 25% losses means 1 in 4 pilots don't come home because their bearing-dependent landing gear collapses on a war-torn runway. By December 1940, the calendar becomes an enemy. Military intelligence estimates Germany will complete its Soviet invasion plans by spring 1941. America must arm itself and supply 2 allies across an ocean patrolled by submarines. Current industrial capacity can't meet 40% of projected bearing requirements, and that percentage assumes Swedish shipments continue uninterrupted. Military procurement officers calculate they need 127 million bearings in 1941. Available supply totals 51 million. The 76 million bearing gap represents thousands of incomplete tanks, hundreds of undeliverable aircraft, and dozens of merchant ships that will never sail. Then an unlikely proposal arrives from a mid-sized company in Canton, Ohio. The letter comes from Henry Timken, president of Timken Roller Bearing Company. His message is audacious. The military doesn't need ball bearings at all. Our tapered roller bearings can exceed ball bearing performance in every military application while being manufacturable entirely from American resources. Defense procurement officials dismiss it as corporate opportunism. Timken makes bearings for railroad cars and heavy trucks, not precision military equipment. What could a company known for simple industrial components possibly offer to solve America's most critical shortage? Henry Timken doesn't come from the elite engineering establishment. His father, also named Henry Timken, was a German immigrant carriage maker who became obsessed with friction after breaking countless axles hauling freight across Missouri's rough roads in the 1870s. The elder Timken patented the tapered roller bearing in 1898, founding a small Canton factory to manufacture bearings for horse-drawn wagons. While European engineers chased ball bearing perfection, the Timkens focused on a radical alternative: cone-shaped rollers that could handle both radial and thrust loads simultaneously. While others focus on making perfect spheres, the younger Timken examines why military applications destroy bearings so quickly. He requests failure reports from the Army's Saginaw ball bearing tests. The data reveals something unexpected. Most military bearing failures occur not from wear, but from overload. When a tank crashes through a concrete wall, the impact shock exceeds the bearing's load capacity. When a bomber lands on a carrier deck at maximum weight, the instantaneous force crushes the contact point between ball and race. Ball bearings fail because the geometry concentrates all weight on a tiny point of contact. Imagine balancing a bowling ball on a marble. Under extreme military conditions, that point of contact becomes a failure point. Timken's tapered roller design operates on different principles. Instead of ball-on-race point contact, the rollers create a line of contact along their entire length. The load distributes across a strip of metal rather than a single point. Imagine the difference between wearing stiletto heels versus work boots while standing on your foot. Same weight, vastly different pressure. This geometry means tapered roller bearings can absorb 40% more shock loading than ball bearings of equivalent size. They're inherently more robust for military punishment. The military establishment remains skeptical for good reasons. Tapered roller bearings are larger and heavier than ball bearings. Weight matters desperately in aircraft design. Every unnecessary pound reduces range, payload, and performance. Navy admirals note that ball bearings allow machinery to spin faster with less friction, critical for destroyer turbines and aircraft propellers. Timken bearings seem like obsolete technology from the railroad era, too crude for modern warfare's precision requirements. But Timken realizes something revolutionary. Military equipment doesn't need the absolute lowest friction. It needs predictable, sustainable performance under abusive conditions. A ball bearing might generate 15% less friction in perfect laboratory conditions, but that advantage evaporates when the bearing operates in dirt, sand, saltwater spray, and temperature extremes ranging from -40 to +160 degrees Fahrenheit. Tapered roller bearings' simplified geometry makes them more tolerant of contamination and misalignment. The gap between adjacent rollers allows debris to pass through rather than jamming the mechanism. This worse is better insight contradicts everything precision engineers believe, which is exactly why European bearing manufacturers never pursued it. The key breakthrough comes when Timken's engineers apply this principle to aircraft landing gear. They design a landing gear bearing assembly that uses two opposed tapered roller bearings mounted in a specific configuration. The opposing angles allow the bearings to absorb both the vertical impact of landing and the horizontal forces when the pilot applies brakes and the plane lurches forward. Ball bearing designs require 3 separate bearing units to accomplish the same function. Timken's solution weighs 6.3 pounds versus 8.7 pounds for the ball bearing equivalent. The heavy railroad bearing actually saves weight in real aircraft applications through smarter engineering. Initial tests reveal challenges. The first prototype bearings seize after 40 hours of testing because Timken's manufacturing tolerances are designed for railroad speeds of 60 miles per hour, not aircraft wheel rotation speeds exceeding 2,000 RPM. Engineers must develop new grinding techniques to achieve the necessary surface finish. The heat treatment process requires adjustment. Too soft, and the rollers deform under load. Too hard, and they crack from impact. After 17 iterations, they achieve bearings that survive 1,200 hours of testing without failure. That's 50% longer than the Swedish ball bearings they're designed to replace. Scaling production presents the real challenge. Timken's Canton factory employs 2,400 workers producing 8,000 bearings per day for civilian applications. Military requirements demand 185,000 bearings per day by 1943. Timken needs to expand capacity by 2,300%, while maintaining precision tolerances and training thousands of workers who've never manufactured precision components. Henry Timken makes a bold decision. Instead of building one giant centralized factory, he'll create a distributed network of specialized facilities. Timken constructs 6 new factories across Ohio and Pennsylvania between January and September 1941. Each facility specializes in one component of the bearing assembly. The Columbus plant grinds inner races. The Gambrinus facility produces outer races. The Canton factory focuses on manufacturing the tapered rollers themselves, the most critical precision component. This distribution strategy reduces bombing vulnerability and allows each plant to optimize for its specific task. The company hires 11,000 additional workers, including 3,800 women, who prove exceptionally skilled at the precision grinding work that determines bearing quality. The training program becomes legendary in American industry. Experienced Timken machinists spend 3 weeks teaching new workers to achieve the required precision. They develop visual inspection techniques using specialized lighting that reveals surface imperfections invisible to the naked eye. Workers learn to hand-select roller sets, measuring each component with micrometers and grouping rollers by size to within 0.0002-inch tolerance bands. This hand-fitting process seems impossibly slow. Each bearing requires 6 minutes of skilled labor versus 2 minutes for mass-produced ball bearings. But Timken's distributed factory system allows parallel production at scale. By June 1941, daily production reaches 47,000 bearings. By December, as Japanese bombs fall on Pearl Harbor, Timken hits 93,000 bearings per day. The first real test comes not in combat, but in the Mojave Desert in August 1941. The Army's Aberdeen Proving Ground wants to evaluate tapered roller bearings in the M4 Sherman tank's final drive assembly. They install Timken bearings in 3 prototype Shermans and subject them to the most brutal testing imaginable. The tanks drive 1,200 miles across desert terrain at speeds up to 26 miles per hour while carrying maximum combat loads. They crash through concrete barriers simulating building walls. Engineers tow them through sand pits designed to jam the suspension. After each 200-mile interval, inspectors remove the final drive assemblies and measure bearing wear using precision gauges. If this test fails, the entire tapered roller program collapses. The Army has invested $23 million in Timken's expansion based on promised performance. If the bearings can't survive combat conditions, there's no backup plan. Swedish ball bearing supplies remain unreliable. Germany's U-boat campaign intensifies throughout 1941. The stakes extend beyond military hardware. If American industry can't solve this problem, the industrial democracy model itself looks weak compared to Germany's centralized war economy. The Shermans complete 1,200 miles of abuse. Inspectors disassemble the final drives and examine the Timken bearings under microscopes. The wear measurements show results nobody expected. The tapered roller bearings exhibit 0.0008 inches of measurable wear on the races. The equivalent ball bearing tests from 6 months earlier showed 0.0034 inches of wear over the same distance. Timken's bearings last more than 4 times longer under identical conditions. The robust geometry that seemed crude and old-fashioned proves superior for military applications. The test exceeds all expectations so dramatically that the Army orders retests to confirm the results aren't measurement error. On February 23, 1942, 3 M4 Sherman tanks equipped with Timken bearings throughout their drivetrains deploy with the 1st Armored Division in Tunisia. These tanks represent the first American armor to face German forces in direct combat. The terrain is brutal. Sand infiltrates every mechanical system. Daytime temperatures reach 120 degrees, and nighttime cold causes metal contraction that would seize inferior bearings. German Panzer IIIs and IVs have been fighting in North African conditions for 18 months. Their crews know how to exploit mechanical failures in enemy vehicles. The Shermans engaged German armor near Kasserine Pass on February 27th. The battle lasts 14 hours. American tanks maneuver continuously, their drivetrains subjected to the exact shock loads and contamination that destroys conventional bearings. When the battle ends, maintenance crews inspect the vehicles, expecting catastrophic bearing damage requiring replacement. The Timken bearings show minimal wear. More dramatically, the continuous operation that would have destroyed ball bearings after 400 hours barely affects the tapered rollers after 800 combat hours. Field commanders file reports praising the Sherman's mechanical reliability, a phrase rarely associated with American tanks early in the war. Within 6 months, data from multiple theaters confirms the pattern. Sherman tanks equipped with Timken bearings achieve 2,200 operational hours between major drivetrain maintenance versus 720 hours for earlier models. The difference translates directly to combat effectiveness. A tank that spends 30% of its time undergoing repairs contributes nothing to the fight. The reliability advantage means American armored divisions maintain higher percentages of mission-capable vehicles. At the Battle of El Guitar in March 1943, General Patton's 2nd Armored Division reports 87% of tanks operational, despite 2 weeks of continuous desert combat. German intelligence officers studying captured American equipment express surprise at the bearing technology. Their reports note that American tapered rollers appear crude compared to precision German ball bearings, yet somehow outperform them. The impact extends far beyond tanks. Boeing installs Timken bearings in B-17 Flying Fortress landing gear assemblies, starting with aircraft produced after January 1942. The bomber's landing gear must absorb vicious punishment. A fully loaded B-17 weighs 65,000 pounds at landing and hits the runway at 90 miles per hour after 10-hour missions over Germany. Early B-17E models using ball bearings experience landing gear failures at rates approaching 8%. Planes returning from raids over Bremen or Schweinfurt limp back to English bases, only to collapse on landing when bearing-dependent gear components fail. These crashes kill more crews than some German fighter attacks. B-17G models with Timken tapered roller bearings reduce landing gear failures to 0.9%. The difference saves hundreds of lives. Pilots report with dark humor that Timken gets you home when Messerschmitts don't. The bearing reliability contributes to the B-17's legendary reputation for bringing crews home despite catastrophic damage. A bomber might return with 2 engines destroyed, the tail shredded by flak, and hydraulics leaking, but the landing gear extends and locks because the tapered roller bearings continue functioning despite the airframe's abuse. Production numbers tell the scaling story. Timken manufactures 23 million bearings in 1942. The figure reaches 91 million in 1943 and peaks at 138 million bearings in 1944. The Canton facilities operate 24 hours daily with 3 shifts. The workforce grows to 28,000 employees, producing bearings for every critical American weapons system. The distributed factory model proves genius when German intelligence identifies Timken as a strategic target. Luftwaffe planning documents captured after the war show Canton listed for potential sabotage operations. But the dispersed production across 6 facilities makes the target too diffuse for effective disruption. Strategic planners realize another advantage. American forces can maintain equipment in forward theaters that would be impossible with ball bearing technology. Tapered roller bearings tolerate rougher handling during field maintenance. A mechanic working in a muddy field in France can install Timken bearings without the sterile conditions ball bearings demand. The bearing's tolerance for slight misalignment and contamination means repair crews can restore vehicles to service faster. This maintainability advantage compounds over time. German Panther tanks might have superior armor and firepower, but they spend 40% more time deadlined for maintenance than Shermans. The technology proliferates to unexpected applications. Navy engineers install Timken bearings in destroyer reduction gears, the critical components that connect high-speed turbines to slower rotating propeller shafts. The bearings must survive depth-charge concussions that feel like underwater earthquakes. Tapered rollers' shock resistance makes them ideal for this punishing application. Fletcher-class destroyers equipped with Timken reduction gear bearings achieve 92% mechanical availability rates versus 79% for earlier classes. In the Pacific Campaign, where every available destroyer screens aircraft carriers from Japanese kamikaze attacks, that availability difference directly affects combat outcomes. By 1945, American military equipment's reputation for mechanical reliability becomes a strategic advantage as significant as production numbers. German and Japanese forces fighting superior quality enemy tanks and aircraft also face enemies whose machines keep running. The Wehrmacht's technically impressive Tiger tanks spend more time being repaired than fighting, because their precision ball bearings can't survive Eastern Front conditions. American vehicles with crude, tapered roller technology fight continuously. The simplicity that European engineers dismissed as unsophisticated proves to be sophisticated in the deepest sense. It works under real-world conditions where theoretical elegance fails. The ripple effects extend to Allied forces. Britain's Rolls-Royce Merlin engine, the power plant for Spitfire fighters and Lancaster bombers, incorporates Timken bearings in several critical applications starting in 1943. Soviet T-34 tanks receive Timken bearing sets through Lend-Lease shipments. Russian tank crews nickname them Amerikanskie podshipniki, American bearings, and hoard them for installation in the most critical vehicles. After the war, Soviet engineers attempt to copy Timken's manufacturing processes, but they struggle to achieve the required precision at scale. The institutional knowledge embedded in Canton's factories proves harder to steal than blueprints. What began as America's most critical material crisis in 1940 became a demonstration of how different engineering philosophies produce radically different results. Swedish and German engineers optimized ball bearings for laboratory perfection, minimal friction, maximum speed, theoretical elegance. Henry Timken's team optimized for reality, shock loads, contamination, field maintenance by exhausted mechanics under fire. The inferior solution proved superior in every dimension that mattered for winning a war. This story proves that the most sophisticated answer isn't always the most complex one. Sometimes innovation means abandoning conventional wisdom entirely and asking what problem you're actually solving. European bearing manufacturers spent 40 years refining ball bearing precision. Timken spent 40 years making roller bearings that could survive punishment. When the crisis came, resilience mattered more than refinement. The 28,000 workers in Canton's factories never saw a German Panzer or flew in a B-17. Yet their precision grinding and careful assembly work directly enabled the liberation of Europe and the Pacific victory. Most never knew that their 6-minute hand-fitting process was literally keeping pilots alive and tanks rolling. Here's what most don't know. After 1945, tapered roller bearing technology evolved into applications far beyond military hardware. Modern automobiles use Timken-design bearings in wheel hubs, transmissions, and differentials. The principle of distributing loads along a line rather than concentrating them on a point makes tapered rollers ideal for vehicles carrying heavy loads over rough terrain. Wind turbines use massive Timken bearings to support multi-ton blades spinning in variable winds. The Mars Curiosity rover's wheels turn on tapered roller bearings designed to tolerate Martian dust and temperature extremes from -126 to +70 degrees Fahrenheit, the same resilience that won World War II now explores another planet. The next time you drive over rough pavement or watch a semi-truck haul freight down the interstate, remember that those wheels turn on bearings descended from a technology born in desperate crisis. Henry Timken bet his company that simpler, tougher solutions would beat elegant precision. The cantilever angles and load distribution principles his engineers developed under wartime pressure now appear in millions of applications worldwide. The small Canton factory that built bearings for horse-drawn wagons became the company that saved American industry when it needed salvation most. Sometimes the heroes of history aren't generals or presidents, but immigrant carriage makers who obsessed over friction and refused to accept that the European way was the only way.